All right, so now is Subspace-Search Variational Quantum Eigensolver. So if we remember that the default one, right, is the knowledge that this expectation value is always going to be greater than or equal to E0. And so how do we find E1? This is limited, right? We can only find E0. But let's say we want to find E1. How do we do that? And so there's a couple of ways that have been proposed, and I'll link all of these discussions down below. But the first one that I know of is called Variational Quantum Computation of Excited States. It came out in the journal Quantum in 2019, and it proposes to use to minimize the following function. And I'm just talking about this so we can see the trends. This is not what I do. So we have this function. So we have the typical term right here, right? I don't know why it uses, it's kind of a weird notation that it uses, but so we have this term right here. This is these, you can see the similarities between, but then it adds a term here, and so this is for the kth eigenvalue, or I should do E of k. So this is k is any, any of the eigenvalues that exist, and so what it adds is this summation at the end from k minus 1 I equals 0. It has some constant here, and it takes the this k and this ith one. And so what this does, what is it saying? This is saying, well, this is the inner product operation, right? So if these states are orthogonal to each other, then this is 0. If these states are the exact same, then I should write this state is 1. And it could be in between, right? It doesn't have to be those. So this can be measured. If I were to do this in Tensorflow-Quantum, they just released a Tensorflow-Quantum.math.ops, which has an inner product operation, and so you could calculate this. However, that's not always easy to do. You have to estimate the state because you don't have direct access to this wave function, so that's not always a fun process. And so what I'm doing in this work is, or what I'm implementing, is the SSVQE, which was proposed in 2019 after the VQE for excited states. So rather than constraining, this is sort of like the rather than constraining it as some sort of in the optimization process, it just builds it into the initial point. So rather than having this term right here, it drops that entirely, and it says, okay, we're going to minimize one function, one initial state. And so based on the fact that there's one basis here, that we're going to just start off and have a set of inputs. It should really just be, we have a set of inputs, and these, this is for however many k eigenvalues we want, and these inputs are orthogonal to each other. Or let's see if I can write this. And so here, this is the Kronecker delta, which means that for that's really common in quantum. If you haven't seen it before, it means 0 if I is not equal to j, 1 if I equals j. And so all this is saying is, okay, rather than using orthogonality as an optimization process or incorporated into that, we are just initializing our entire function to be orthogonal. And this is easy to do, remember, because if we have some quantum state vector, let's consider it a 1 qubit case, right? This is 0, and this is 1. We can clearly see, okay, if we just want to initialize this for the 1 qubit case, we can find there's only two eigenvalues for any 2 by 2 matrix. So we can say, hey, wait a minute, let's simply just, put a Pauli x value. So we could have our first Hamiltonian be, so there's two parts to this. So we have the k eigenvalues we want for this Hamiltonian, right? And so then this goes into k arms. So this might be 1, 2, 3, and then each one of these is a VQE in itself, sort of circuit that has, decompositions of its own. And so when we break this down, right, when we say, okay, it's for the kth eigenvalue, each one of these processes has decomposition. So just keep that in mind. And so what does the optimization look like? Well, we try to that is not the best. We try to minimize the following loss. Once again, the parameters are shared because it doesn't matter that for decay eigenvalues, it doesn't matter that the parameters have to be shared because this input is the same, and because we're enforcing this orthogonality, we can guarantee that these will be the different states. Before I actually say the loss function, though, I realize I should clarify one thing. For any matrix, if we have the eigenvalue problem here, this is the eigenvalue problem, or eigenvalue eigenvector problem. This, if A is Hermitian, so if A is Hermitian, I forget, this dagger is a symbol, right? Then the eigenvectors, to give you some intuition behind this, for any Hermitian matrix, the eigenvectors are orthogonal. So in quantum mechanics, right, because this is a Hamiltonian, this is a measurement operator, or when we're approximating, this is a some system, right? Any operator, any quantum mechanical operator is Hermitian, and therefore the eigenvectors are orthogonal. And this, you see Hermitian matrices come up all the time because the eigenvalues of Hermitian matrices are always real, and that's important, right? Because if you're making a measurement in quantum mechanics, and you can't measure I don't know what it would mean to measure an imaginary value, and so that's good. But the eigenvectors being orthogonal is also important because the eigenvectors are these states that the wave function is in. So if they weren't non-orthogonal states like that, there's physical description of realities there that wouldn't make sense. And so we can say, okay, this makes sense because if this orthogonality constraint makes sense in this context of Hermitian matrices, especially considering that their eigenvectors are all orthogonal. That's just something to note, I guess. So now we can actually get into the exact loss function that we are minimizing in this situation. So once again, it's the sum over to k. However, whatever k order eigenvalue that we want to create. And so here we have slightly different notation. And so this is the technique that I used in the Penny Lane quantum hackathon. And I discussed it a little there, but this is just more in depth. And so remember previously we could write the normal. This is the standard, right? This is the standard variational quantum eigensolver. We're starting with the 0 state, and then we're applying this U circuit. As if this is just saying we're starting with a given state, and so these are just the different states. That's all that's different. And notice that Wj is or maybe if I do the list of W's, they're decreasing. So for each value, Wj is less than Wi for j greater than I. And so this is just an optimization process, right? We have this decomposition, and for this gives us, by the way, all k eigenvalues. There's processes in the paper, which I'll link, the Subspace Variational Quantum Eigensolver, which for just a specific k value, but this optimizes all of them simultaneously. So we can see that here. The circuit is slightly different. This is the closest. I'm trying to get closer to the VQE 500 problem, where that used the rotation, arbitrary rotation, but you can decompose any unitary rotation into Ry or ZRy. And so that's what I do. And it's very similar to the previous one as described here, except the difference is we just have Ry, Rz, Ry for every qubit, and then we have the controlled C naughts, or the controlled X gates. However, there is one additional X gate right here that wasn't there before, but other than that, very similar. And then we have the this is exactly the same code. This is the same code for the Hamiltonian readout, same code for creating VQE. The only difference is, no, actually this is all the same. The product, this is the same, actually. It is not the exact same, because that's not as efficient. So I will just copy that over. Now it's the same. And the real min, this time we had a k function for the k eigenvalues. This will give us the k lowest, but other than that, it's the exact same. And now we can see this is the difference once again. Here we have the variational quantum eigensolver layer, which is exactly the same as before. However, it does not manage its own weights, because remember we created a VQE layer to share weights between decompositions, but now we want to share weights between every single VQE and all of its decompositions. And so we create a master, VQE, SSVQE that manages the weights here. And so then we, for each of the k Hamiltonians, this is exactly the same, by the way, the call is the same. Everything's the same, it just doesn't manage its own weights in this VQE layer. And in this layer, however, we initialize it, we keep track of the weights, we keep track of each of the VQE, or the sub-Hamiltonians, the kth eigenvalue VQEs. So we create however many we need, k VQE layers here. And then for the call, right, we this is not, unlike the VQEs, this isn't one output that we need to that has any meaning. It's just something we're minimizing. It's not something that is the actual energy. So that's an important note. It's not this. We're not minimizing the energy directly. This is sort of a pseudo sum of all of the energies that we're minimizing. And so we can see that for each time we do a feed forward, of the we feed the input of the input and the weights. And notice the inputs once again are always just going to be circuits blank. And then we add the weight. This is the exact same relative weighting I used. I just used one weight for the initial one, 0.65, 0.55 for the next two. I only used 3 eigenvalues in this one. I guess you could do more. You might have to adjust the code slightly. And we return total. And we also return all of the calls because these are the actual eigenvalues or the energies that we're calculating. So that will be important to calculate. Here are some examples. These are the 2 Hamiltonians from the hackathon. These are the exact same ones that we used. So then once again, we create the qubits. We do layers. So this time it's just 3 times q times layers because we have 3 parameters per qubit. We initialize the components, and then here we say, okay, I want to find the top 3, or sorry, the lowest 3 eigenvalues. And so the way we do it is this code is exactly the same here as before. The readout ops are the same. The expectation value cost is the same. Remember, the reason we just can do a sum here in this VQE call is because the readout ops have the weights built into them. And so then we can, the only difference is that for the ground state, right, this is exactly the same, but for higher states, we need to make them orthogonal, but this is trivial to do in quantum because we can just apply the Pauli X gate to a qubit, right? We can just say, call an X on that qubit, boom, orthogonal state. And so that's just the input circuit, but that's already built into the VQE model. So that's why all of the inputs are still just normal circuits. It's because the orthogonality is built in. Then we create the SSVQE and we set the outputs equal to this 0 because that's what we want to minimize. We create the real minimum for the K values. We set the optimizer here. We're just keeping track of the values. And this is why we have the other output, is because we reinstantiate the layer, and then we just every time we just set the variables, set these weights to be the same as the model, and then we can get the exact energies by using this output. So that's how we're able to get the energies, right? Is we know the values of the weights here. And so that is why we return this calls, even though we don't use it in the optimization. And so then we can see this process, we just output it and then we print the each of the curves. So first, you might notice I had a commented out section because the orthogonality isn't always exactly the way we want it, right? Every orthogonal state will give you a different eigenvalue, but if you want the lowest 3, it's not always the exact same orthogonality inputs. So in this case, and another thing here, we can see we're using expectation values rather than sampling. I'll change that real quick, actually, just for show, and we can go over and we can run this code, and it takes a minute to run, so I'm going to pause. Okay, so you can see the optimization process is complete, and I will now show the graph, and I apologize in advance that the colors do not match. That was too much work. Making colors match too hard. So we can see that this is able to, you can see the colors don't match, so ignore the colors. All that matters is that these 3 parameters were able to minimize and go to the 3 lowest eigenvalues pretty well. And so this is the first of the first Hamiltonian given, but this is it's a cool graph, I think, actually. And so we can see, yep, it is in fact able to learn the parameters. So now we can run the second example, and I will run that, and Let's go on. I will run that, and I will pause now, and I will run its own course, and we can see that at the end. Okay, it has finished. Just a heads up, I changed the optimizer to Atom with learning rate 0.1 because it was more stable in this case. But now I will show the graph. And so this was the second one, and you can see once again able to learn the 3 lowest eigenvalues. So it's pretty cool. So that's the SSVQE and Tensorflow-Quantum using 2 custom layers, able to find any k lowest eigenvalues. I don't actually think it has to be lowest. You know, you could think you could pick your orthogonal states differently, but maybe not. And so yeah, code and papers are there also. So